I wanted to explain some solutions to the homework set that we just turned back, the assignment on linear growth. Most of you did really well, but I just wanted to talk about some of the ideas that I tried to mention when I graded it. So this first thing is the education expenditures chart. And the first thing you notice is the vertical axis is billions of dollars and the horizontal axis is years. But I asked you, there are two ways to to put a variable for the horizontal axis. You can either pick x equals the years, so the first one would be x equals 1990 and the last one would be x equals 2004, or you can decide to pick smaller numbers and let x equals 0 be your start, and your start is years after 1990, for example, all right? So you can decide whatever you want the x value to be. So that first point, either x is 1990 or x is 0. There are options you can have for that. So I chose x equals 0, and that means the other point is x equals 14 years later. And so you can find a slope, and the slope is, like we've done in a lot of examples, the rise. The last point is $536 billion, and it started at $248 billion, so the increase is $288 billion, and that took 14 years. So that's $20.57 billion per year. And a lot of you had trouble making an equation. And so the equation should be, here's the formula for an equation in terms of x, and you can plug in whatever point you want. If you plug in the point 14,536, you get this equation, y minus the y value equals the slope times x minus the x value. Or you can plug in the other point, 248 and 0, and you get a different form of the equation. But if you simplify them both and multiply things out and get it in the y equals mx plus b form, the b's end up being the same and you get the same equation. So it doesn't matter which point you choose for your point of using the point slope formula. But once you have that equation, you can solve things. And so I asked you, when is the total spending going to equal $1 trillion? And first of all, remember that you only have to plug in the y value equals 1,000, because your units are billions of dollars. So $1 trillion is 1,000 billion. And if you set that equal to your equation, you can just solve by subtracting 288 minus 288 minus 288 over here, and you get 712. Then divide by 2057, and you get x equals 34.6. And in our case, that represents years after 1990, so it's 2024. The 0.6, it's just an estimate, so that might mean a little more than halfway through the year, but this is just an estimate. So it's in the year 2024, approximately. But remember, your linear equation was just an approximation. That back here, we talked about, this really isn't a linear function. It looks like it's increasing faster and faster, so maybe a better line would be something like that. We could talk about better models. Right? Maybe it's not linear. Maybe that's not the best approximation for what's happening with the data. Similarly, if we talk about the marathon times problem, this is the graph that you've got, and what you want to look at is the vertical axis is over here. The vertical axis right now is in hours colon minutes, and if it's in a mixed units like that, that's going to be awkward for any equations. So you really want to switch it all to minutes, which I've done over here, or you can switch it to hours and have like 2.5 hours for here in the middle. But it seems like minutes makes more sense for this problem. And again, the x-axis is years, but I chose it to be a starting point of 1900 was the start, right? And so you can find, I picked 2 points here, this point up here, 10 and 167, which means the year 1910, the time was 167 minutes. And over here I picked 100 years after the start, the time had dropped to 125 minutes. And so that gives you a slope equation. the change in the minutes over the change in the years, and that comes out to minutes per year, negative 0.46 minutes per year. So it's decreasing at about a minute or half a minute every year. And the women's slope, I can do a similar thing, and I pick 2 points, and I find an equation for that. And so in between 75 and 100, so in 25 years, it decreased from 166 to 135. So that's 31 minutes in 25 years, which is 1.24 minutes per year, which is great. But I wanted to point out, you could have chosen other equations or other points for these. So some of you picked like this point and this point, and does that slope represent the whole data? Maybe, maybe not, because it doesn't really capture all this data over here. Some of you, nobody picked this, but the worst case would have been to pick these 2 points, and that line doesn't represent the data at all. So you want to find one that represents the data in some way, and I tried to do that with the orange. There are formal ways to do that with what's called a linear regression line, but just for us, we're going to kind of eyeball it and trying to find one that represents the graph. And we might talk about this later. Represents the graph. So once you have those slopes, how do you find equations? Well, you can find equations like here, doing this y minus the y value is equal to the slope minus 0.46 times x minus the x value. That means it started at 167, and every year after 10, however many years that's been, you multiply by the rate per year to get you the change in the y value. And so you can then take that equation and simplify it if you want to. The women end up with an equation over here. And so now that I have 2 formulas, I can use that to predict lots of things. So the example they asked is, when will the men's record equal the women's record? So you set the men's record equal to the women's record, and you solve for the year. And that comes up with 2012 if you do the calculations. And so if you go back to our chart, erase all this other bad stuff, our 2 lines look like they cross down here someplace, right? And that's about 120 years after the start. Our formulas said that it's actually 112. So my lines aren't exactly straight. The calculations come out to that. So I hope you can set up an equation like that and then use it to solve whatever you need to. One other thing that I wanted to mention is we are just using lines as an approximation for this data. Maybe that's not the best example. Maybe this data, the men's record, seems to be decreasing quickly here, slowing down, and then leveling off. So maybe it's more of a curve like this, which might be an exponential curve. And we'll talk about that in a few weeks. The women's, on the other hand, might also looks to be leveling off. It's not likely that this continues forever, because that says in like 100 years, in the year 2100, they should be at like 1 hour and 30 minutes, which really is almost certainly physically impossible. That's Usain Bolt running his 100-meter dash time for an entire marathon. That's not going to be possible. Realistically, the times are going to level off. And that might be a different sort of curve, an exponential curve, rather than a linear curve. And we'll talk about those later.